Okay, we're going to just continue on reviewing, I guess. So we finished up there in we're in the middle of talking about chapter 11, I think. So we talked early on in chapter 11, like we talked about a second ago, about waves. It really led to our conversation about electrons and where they are in the atom. Remember that electrons can be found on different energy levels. And as they transition up to a higher energy level by gaining electrons, eventually they will want to work themselves back down to a lower state of energy. The result of that is they will give off that energy in the form of a photon of light with a specific wavelength. And if that wavelength does correspond to some parts of what we talked about, which is the electromagnetic spectrum, where we had things like radio waves over here, some microwaves. We also have the visible part of the spectrum. That's where we see color. Right, or Roy G. Biv, right? We also have UV, maybe some gamma rays, some X-rays in there. And remember that this part of the spectrum on the left there where the gamma rays is short wavelength and high energy. And the other side is obviously longer wavelength and lower energy. And if it did fall in that sort of visible part of the spectrum, where even the colors have sort of ranges of energy, where violet is the most energy, or highest in energy, red is lowest in energy, we will see different colors. So kind of like when we did our flame test experiment and you put the elements sort of into the flame and excited all the electrons. Electrons go up to a higher energy level. They work their way back down. They give off that energy and you see different colors in the flame. Our fireworks as well works kind of the same way. You explode the fireworks with the elements. Electrons go up higher, come down, and we see different colors that occur. This led us into really a talk about where we find electrons in the atom. And ultimately, we find electrons in what are referred to as orbitals. And there are different types of orbitals. There are s orbitals, p orbitals, d orbitals, and f orbitals. The s orbitals begin on the first energy level, n equals 1. N is the energy level or the principal quantum number. And then all other energy levels, there's s orbitals. When you get to the n equals 2 level, that is where you first see p orbitals appear. And when you get to the n equals 3 level, that is where you see the d's appear, and f happens on the 4th energy level. Remember that all electrons can be found in an orbital, and any individual orbital could hold a max of 2 electrons. So that's the maximum it could do there. In terms of s orbitals, there's only one type, which means if you max out an s orbital, you will end up with 2 electrons total. There are 3 different types of p orbitals, which means if you max out all the 3 types of p orbitals, that is 6 electrons. And that means that this is what is sometimes referred to as a subshell or a sublevel, the 3 p orbitals together. D orbitals, there are 5 different types, which creates a d subshell, and you can max out with 10 electrons. And f orbitals, there are 7 different types, which would max out at 14 electrons. This is really important in terms of writing electron configuration, and there is a certain order at which electrons go into the atom. And we talked about that order, and that's something that you could create pretty easily for yourself on the paper. And let me do that. I won't write too low in here because I know it's hard to see. So you could recreate that by just going, okay, S's start at 1, P's start at 2, D's start at 3, and F starts at 4. And you basically just fill in the numbers underneath there. So that would be 2s, 3s, 4s, 5s, 6s, 7s. And then obviously fill in the rest of these guys here with the right numbers. 4p, 5p, 6p, 7p, 4d, 5d, and 6d, and 5f. And this is the order at which the electrons go into the atom, and we basically start at the arrow and keep zigzagging back and forth there. And this gives us an electron configuration or something, say like we'll do our friend sodium there, which is 11. And it would be something like 1s2, 2s2, 2p6, 3s1 in this case. These here are what are referred to as core electrons, right? They are closer to the nucleus. This is the valence electron, which is the outermost and highest energy level electrons. We also talked about that we can draw what is referred to as the orbital diagram for these guys. And that's either a box or a line to represent each of the orbitals. So 1s, 2s, obviously the 2p subshell would have 3 boxes, one for each of the p's, and then one for the s here. When they do go into the orbitals, they do go up first, right? Followed by down. That is what is referred to as being paired spin for those electrons going opposites of each other, up, down. When they go into a subshell like a p, they do go in one at a time. The idea here is to maximize parallel spin, and then they come back and pair off. And then we would have that right there, which would be our orbital diagram. Question on that there. Now, obviously, we talked about a couple of different ways as well. We could do sort of a shorthand for this, as this part of the configuration is 10 electrons, which would be neon in this case, and 3s1. So again, we kind of always put a noble gas in the little brackets there, and then continue on with our 3s1. Any questions on that there? Now, if something has a charge, right? So if we had a sodium with a +1 charge, in this case, it has a +1 charge, which means it lost 1 electron, which means he would actually only have 10 electrons. Its configuration would be 1s2, 2s2, 2p6, or that would be neon. Remember that representative elements, when they gain and lose electrons, the goal is really to end up like a noble gas. So in the case of sodium, it loses an electron and ends up with the same configuration as neon, which is the noble gas comes right before it. Things with the same electron configuration, neon and sodium with the +1, are what are referred to as being isoelectronic with each other. They have the same electron configuration. Obviously, if something had a negative charge, we would need to add electrons to our total there to compensate for that. Any questions on electron configuration? We also talked about, I think in this chapter as well, towards the end, some periodic trends when we were doing those experiments. So we talked about some periodic trends. And the first one that, or one of the ones we talked about, was size. So size decreases as you go to the up and right, and increases as you go left and down. We also talked about what is referred to as ionization energy. And that increases as you go up and to the right and decreases as you go down. ionization energy is the energy required to remove an electron from the gas phase. Another trend that we talked about was electron affinity. It increases as you go up to the right and decreases as you come down. Electron affinity is the energy change that occurs when we gain an electron, when an atom gains an electron. Not to be confused with electronegativity, which also has a similar trend. Electronegativity increases as you go up to the right and decreases as you go down. Electronegativity is the ability of an atom to bring electrons towards itself. Remember that fluorine is the most electronegative, which is up this way. Fluorine is the most electronegative element you could have. All of these trends that we talked about basically lead to what we know happens, which is as we go up and to the right on the periodic table, these guys tend to lose electrons, which makes sense because there are nonmetals. And when we go kind of down and to the right on the periodic table, they tend to, I wrote that backwards. They tend to gain electrons up here, sorry. They tend to gain electrons or nonmetals, and our metals tend to lose electrons. There we go. That's more correct there. Our metals. Thanks, guys. Any questions on any of those periodic trends there? I think that wraps up chapter 11, if I'm not mistaken. Any questions? No? Yeah. All right, then we got into chapter 12, which was bonding. That's fun stuff. So let's talk a little bit about that there. Chapter 12 is bonding. And there's really two types of bonding. There are ionic bonding, which is always between a metal and a non-metal, where we have a transfer of electrons from the metal to the non-metal. There's also covalent bonding, which is between two non-metals, where we have sharing of electrons. And as we talked about, that sharing may be equal. And if it is equal sharing, that is what is referred to as a nonpolar covalent bond. And if the sharing is unequal, that is what is referred to as a polar covalent bond. What determines whether or not the electrons are being shared equally or unequally is the electronegativity. For a covalent bond, and we could do the difference in electronegativity. So for example, hydrogen is, we'll go at roughly 2.1. Fluorine has an electronegativity value of 4. So if we do the difference in electronegativity, it is 4 minus 2.1, which is a 1.9 difference. And when we do the difference in electronegativity, anything from 0 to like 0.4 is a nonpolar bond. Anything from like above 0.4 to below 2 is a polar bond. And anything typically, not always 100%, but anything above 2-ish is ionic. So those were those cutoffs that we could use with the electronegativity values that we saw in that table. A reminder that you a lot of times don't necessarily always need those values. You could use the actual trend of electronegativity on the periodic table to help you decide that, especially if you're comparing two things that are in the same row or two things that are in the same group. You could just go by that and figure out it should be probably a polar bond that would happen in there. Remember that we use electronegativity values for bond polarity, which simply tells us between those two elements in that one bond, is that bond going to be polar or nonpolar or ionic? It's not molecular polarity, which again is something else we also talked about in this class. These three types of bonding are sort of at one extreme to the other. So on one extreme, you have ionic bonding, where we have absolutely no sharing of electrons. It's the positive negative attraction that holds that together. On the other end of the extreme, we have perfect equal sharing of electrons, which is a nonpolar covalent bond. And sort of in the middle, we have a polar covalent bond, which is not a complete transfer of electrons, but not sharing equally. So sort of in between. They're still sharing electrons, but definitely not an equal sharing of electrons. Any questions on that? Yes, sir. So above 2 is ionic. Yeah, above 2 is ionic, and that 2 cutoff is not perfect. There are combinations of, if you see like a metal and a non-metal, if you look at the electronegativity value table and you subtract it, you'll get like under 2 in some cases. But it's sort of a rough estimate, that too. Remember, though, that pretty much if you have a metal and a non-metal, it's always going to be ionic. So regardless, you really don't even need the electronegativity value table to tell you that. As soon as you recognize it as a metal and non-metal, it should definitely be ionic in that case. Yeah. Other questions? Yeah. Yeah. So if you are, I'll draw it on the next page so it's a little higher. If you look on the periodic table, right? So my very skinny periodic table here, apparently. It increases electronegativity as you go up and to the right, and it decreases as you go down, which means if you are comparing two things that are pretty much in the same row, yeah, so they're in the same period, the guy that is further to the right should be more electronegative than the guys further to the left, which means you really don't need the numbers. That will result in a polar bond. And if you are comparing elements that are basically in the same group, you could also do that, because the guy again further up in that group should be more electronegative than the guy further down in that group. So once again, it should result in a polar bond. So definitely, if you got two things that are same period or same group and you're comparing them and want to know, is it going to be polar or not? It probably will be polar if they are in that sort of situation. And which way the electrons will go is, again, the one that's further to the right or the one that is further up in the group would be there. So remember that when we look at something like HF, we could draw that dipole arrow where it points to the one that's more negative, right? And the other guy is more positive. Because of that unequal sharing in a polar bond, we create partially negative charges and partially positive charges that occur here on those two atoms within it. So if you were looking at something like, say, nitrogen and oxygen, and you want to know, hey, I got a bond between these two things, is it going to be polar? When you look at the periodic table, oxygen is further to the right, which means it should be more electronegative than nitrogen, and you would probably result in a polar bond heading that way, as opposed to, as well, if you did like oxygen and sulfur, for example. Again, sulfur is lower there, which would mean it is less electronegative. So once again, it would point, towards the oxygen side. Other questions on that? Okay. So we also talked about in this chapter, besides that we talked about actual drawings. So we could represent bonding through the use of Lewis dot symbols or electron dot symbols. And we basically do 1 dot for each valence electron. There's really no big rule other than the fact that we should not put more than 2 dots per side when we draw these shorter structures. Each dot represents a valence electron, and the number of valence electrons equals the group number on the periodic table. So everybody in group 1 has 1, everybody in group 2 has 2, and so forth as you go through there. So magnesium has 2 valence electrons. We can show ionic bonding through the use of this. If we look at, we'll take magnesium, why not? We'll take magnesium and we'll put it with oxygen, which is group 6. So it has 6 valence electrons. Again, the configuration for magnesium would be neon 3s2. 3s2 is the valence electrons. Those are the 2 dots that we see there. For oxygen, it is 1s2, 2s2, 2p4. It is the 6 electrons here that are the valence electrons that we see. Because this is a metal and a non-metal, we would expect our magnesium to do the right thing and give up its electrons basically over to the magnesium. The result of that is we will then end up with a magnesium that has lost 2 electrons and becomes positively charged. We will also end up with the oxygen, which will pick up those electrons and become -2 charged. The result in terms of the electron configuration is magnesium will get rid of those 2 electrons and end up with neon's configuration. The oxygen will put those 2 electrons right there and end up as 1s2, 2s2, 2p6, our neon's configuration. And again, as we talked about, really the goal of all bonding, whether it is ionic or covalent, is for everybody to achieve the same electron configuration as a noble gas. And in the case of ionic compounds, they do so by the metals losing electrons and they back up to the noble gas that comes right before them. And the non-metals will pick up the electrons and go forward to the noble gas that comes after them. Any questions on Lewis symbols here for ionic bonding? We also talked about drawing covalent compounds or molecular compounds using Lewis structures. And there's several steps. So if we were going to draw something, we'll go with like an F3. The first thing that you want to do is count up the total number of valence electrons. So nitrogen is group 5, fluorine is group 7, and there's 3 of them. That gives us 26 valence electrons. That number is important because we do want to make sure our picture has exactly that number of electrons. The one that should go in the center is always the least electronegative atom. So the least electronegative should find itself in the center. Remember, fluorine should never be there, nor should hydrogen. We then would put our other guys around and we would make a single bond to each of the outside ones, counting up the electrons, which is 2, 4, 6, gives us 20 more electrons to go. We're going to fill up the outside ones until each of the outside ones meet the octet rule, which means it has 8 valence electrons. The exception obviously is hydrogen that should only have 2 electrons total. At this point, we put 24 electrons on our picture. We still have 2 more to go. They should go on the center one in pairs as well. At this point, all 26 electrons have been put on there. Everybody meets the octet rule, and this would be the proper Lewis structure. Sometimes you do need to make a double bond or triple bond to fix a situation where you do not reach 8 electrons. So if we drew NO3 minus, that is 5 plus 3 times 6 plus a 1 for the negative charge. That's 18, 19, 24 electrons. We follow the same pattern there, nitrogen in the middle. We're going to do oxygen, oxygen, and oxygen. We're going to do a single bond to each of them. Once again, given us 6 that we've used. We have 18 more to go. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, we have put in all of our electrons. And our nitrogen is not good because it only has 6 electrons. So again, this is the point where we would make a double bond to do so. Remember that when we make a double bond or even a triple bond, we're actually taking a pair of electrons and we're going to move them in. And that's what's going to help us keep the right number of electrons. This would give you a picture that looks like this, which would be obviously our correct picture, where we have a total of 24 electrons and everybody is good in terms of the octet rule. You could have, as we talked about as well, when we were doing this, you could have bonded to the left there, you could have bonded to the right and drew another couple of structures. Those are what are referred to as resonance structures, where it's basically the same guy, except that you chose to do the double bond in a different location, like this guy here. Again, these two guys would be resonance structures of each other. You could actually draw one more if you wanted to, where we double bonded to the right-hand side. And those would all be equivalent structures. That's because the double bond electrons are moving around. They're delocalized, which means at any given point in time, they may be at the oxygen up on top, to the left, or to the right. So you could draw one of those 3 structures, and they all basically are sort of representative of what's going on. If you're not asked to draw resonance structures, then obviously you do not need to draw them all. But if you are, you basically just move the double bond or double bond around, basically. Any questions on that there? We also talked a little bit about bond strength, right? And it is related to length. A single bond is longer than a double bond, which is longer than a triple bond. And this is the weakest of all bonds, a single bond, followed by a double bond. And the strongest of all bonds is our triple bond. Again, as the distance between the different atoms get closer, everything's held tighter. It is harder to break, again, a triple bond versus a single bond. We sort of finished up talking in this chapter about a couple of things, one being obviously molecular geometry. So in this chapter, we talked about geometry. And really the simplest geometry is if you have a diatomic molecule. And a diatomic molecule is basically like HF or N2. They will always have a geometry that is linear because they are always basically 2 things that is basically at the ends of a straight line. When you get 3 or more atoms, you do have to look at a couple of things. First off, the number of electron pairs around the central atom. You also want to look at the number of bonds to the central atom. This will give you an electron pair geometry. This will also give you a molecular geometry, our shape. And we'll do like an example, I guess. So for example, if we had something that looks like this, we would want to look at the central atom here, and we see that it has 2 electron pairs. It also has 2 bonds, which means the electron pair geometry would be linear. The molecular geometry would also be linear. It's about 180 degrees. And The next geometry that we looked at was a situation where you had a central atom and 3 things sort of attached. Central atom again has 3 electron pairs and 3 bonds. That is what is known as trigonal planar. It's about 120 degrees. The molecular geometry is also trigonal planar. We then had a situation where we had basically 4 things attached here. 4 electron pairs, 4 bonds. That is tetrahedral and tetrahedral for both names. It's got a bond angle about 109.5 degrees. In a situation like all 3 of these examples, when we look at the center atom on all of them, there are no non-bonding electrons, no dots basically, which means 100% of the time, both of these names will be the same, because basically we are dealing with these one type of electrons, which is the bonding electrons that are happening here. By the way, when we do this type of geometry here, a couple of important considerations. If you have a double bond or a triple bond, it counts as 1 electron pair and 1 bond. So double bonds, triple bonds, when you're doing geometry, count as 1 electron pair and 1 bond. We also saw that when we start to introduce non-bonding electrons to the mix, we get a lot of electron-electron repulsion that occurs. We have bonding electrons near bonding electrons, which is okay. We have bonding electrons near non-bonding electrons, which is also getting a little bit worse. But the worst situation as well is when you get non-bonding electrons near non-bonding electrons. They absolutely do not want to be near each other. So when we start introducing these non-bonding electrons, what we start to see is actually a change in the shape of the molecule, because there's not an extra bond there or atom, and there's just non-bonding electrons. What it allows is the molecule basically to move a little bit more, and the overall shape will start to disappear. So since we're getting a little too low on this one, let me write those guys over here. Number of electron pairs, number of bonds, electron pair name, and molecular geometry name here. And we'll do our example here. So for example, if we had something like this guy here, maybe something like this. We look at this here, the central atom now has 3 electron pairs. It doesn't matter if they're lines or dots. In this case, it has only 2 bonds. Something with 3 electron pairs is still trigonal planar for the electron pair geometry. But because of these non-bonding electrons, it allows the overall shape to move a little bit, and we get what is sometimes referred to as an angular shape that occurs in that case. We also can have one like this. Where the central atom has 4 electron pairs, 3 bonds, and 1 non-bonding electron. It has, again, 3 bonds. So something with 4 electron pairs is tetrahedral. But because of those non-bonding electrons and those 3 other bonds, we get a shape that's known as trigonal pyramid. Has a bond angle just less than 109. And lastly, if we have something like this, which is basically like water, we have 4 electron pairs and 2 bonds. Once again, the 4 electron pairs will give you tetrahedral for your electron pair geometry. This is the worst situation. We have non-bonding electrons near non-bonding electrons. we get what is referred to as bent or V-shaped. Also a bond angle less than 109. So for something like water, it's just like 104-ish in terms of the bond angle. So when you do have non-bonding electron or dots on your Lewis structure, the molecular geometry name will differ, but the electron pair geometry name will still be the same based on the total number of electron pairs. Any questions on geometry here? No, you probably don't have to worry about it for the final, I think. So we finished up in this chapter talking about overall molecular polarity. And that is the entire molecule as a whole. And remember that the diatomic molecules are the easiest because they really only contain one bond, which means if you have something like HF, we've already established that this is a polar bond. And because that is a polar bond and it's the only bond that is there, it is going to be a polar molecule. Now, if you had something like F2, this is a non-polar bond, which means because that is the only bond there, this will also be a non-polar molecule. It is when you are dealing with 3 or more atoms, you need to look at 2 things. 3 or more atoms. You need to look at, are there polar bonds? Which would be your electronegativity. And secondly, you need to look at the molecular shape or geometry. So an example that we looked at was like carbon dioxide here. Looks something like this. Carbon dioxide, once again, back to an earlier question, you look on the periodic table, carbon and oxygen are in the same row. Oxygen is further to the right, which means I know for sure this is going to be a polar bond heading towards the oxygen in this case. So even though it has polar bonds, the geometry here is basically 2 electron pairs and 2 bonds, which is linear. And because of that, they're going to basically cancel each other out. It's like a tug of war, oxygen pulling this way, oxygen pulling the other way. Nobody's going to really move. And although it does have polar bonds, this guy is actually going to be a non-polar molecule. So you do have to take into account the geometries in these cases when you have 3 or more and if there's polar bonds or not. Sort of the quicker way of doing it is, and most of the time you will be probably correct, is there are some symmetrical geometries. And what we're talking about is our molecular geometries, which for us would be trigonal planar or tetrahedral. So basically, if you draw these guys, there's no dots on the central atom. These guys will be non-polar if all the outside atoms are the same element. And then we have some unsymmetrical geometries, which is pretty much everybody else. That's going to be our angular, our trigonal pyramid, our bent, our V-shaped. These guys will be polar if all the outside atoms are the same. So if you draw any of those guys, you'll have dots on the central atom. If they're all the same element on the outside, it's going to be a polar molecule. If you draw the Lewis structure and there's no dots and everything on the outside is the same, it will be non-polar. If you draw your Lewis structure and there's no dots, but everybody on the outside is not the same element, it will then become polar. So remember, that's sort of the change that occurs. The only one you really have to worry about is linear because it's a straight line. So if those dipoles are going in opposite directions, they will cancel. If they're heading right at each other, they will cancel as well. But if they're all heading in the same direction, then it will become polar. Question on geometry there. Yeah. Yeah, so no dots on your Lewis structure on the central atom we're talking, so always the central. So no dots on the central atom and all the outside elements are the same element, then it will be nonpolar. If you do no dots on the central atom and the outside elements are not the same, then it will become polar. So that's the kind of switch that can occur with that. And if you draw your Lewis structure and you do have dots on the central atom and everybody on the outside is the same element, it will be polar. Yeah. So just look at that. If you drew, say this guy, no dots on the central atom, there should be dots on the outside, but no dots on the central atom. Everything on the outside is the same. This is going to be a nonpolar. If you take one of those guys and swap it out for like a hydrogen, now there's still no dots, but everybody on the outside is different, not the same. It will then become polar because these guys are going to be electronegative and polar. This guy's going to be nonpolar. So you got like 3 of these guys pulling this way and the other guy's not pulling back the other way. And then obviously if you drew something like water, right? I see dots on the central atom, everybody on the outside is the same, it would be polar. If you did something like NH3, dots on the central atom, everybody on the outside is the same, it will be polar as well. So that's what we mean on that. Question on bonding, geometry, any of that stuff there? That wraps up chapter 12. That was a big chapter, huh? Jeez. All right. Then we rolled to chapter 5, which was another favorite, right? And this was all about naming, right? So this was all about nomenclature. Right? So we talked about different types of naming. We had type 1, which is a ionic compound. And it is a metal and non-metal. And remember that it is always the metal that's most important when it's involved. The metal is a group 1, 2, 3, zinc, cadmium, or silver. What they all share in common is they have fixed positive charge. To name these guys, we use the whole name of the metal. And the non-metal gets the IDE at the end, right? So NaCl, sodium chloride. Then we had type 2, also ionic. Also then means a metal and non-metal. Once again, it is the metal that is most important, and that is basically going to be your transition metals. Are just to the right of the transition metals like lead, tin, lead, tin, etc. These guys have variable charges, so they could form different charges depending on what they're hooked up to. So in these, we have to figure out the charge on the positive guy and use a Roman numeral. So we use the whole name of the metal. We use a Roman numeral. And again, the non-metal takes the IDE here. So obviously, if we had something like FeCl2, we know that Cl is -1, which means in this case, it is iron 2 and 2 of these Cl minuses. That means the name here would be iron Roman numeral 2, not for how many metals you have, but for the charge. And even though you have 2 of the chlorides, it is still just chloride at this point. Question on type 1, type 2. We then got into type 3. Type 3 is two nonmetals together, which is covalently bound. And this is really the one where we use prefixes. So we use prefixes here. And that's like mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and so forth. Here, a couple of rule is we do not use mono on the first name, but we can use it on the second name. And secondly, we sometimes will drop the vowel from the prefix, so we don't get two O's to back up to each other, or an A and an O. So we typically will drop that first vowel. So this one is pretty simple in the sense that you do not have to figure out charges or balancing things. So like N2O5, that would be dinitrogen, whole name of the first element along with the prefix. Second guy gets the prefix. We're going to drop the A here, and it gets the IDE at the end of it. So pentoxide here. And once again, whole name of the first one, prefix on the second. So this would be carbon, no prefix because there's just one, monoxide here. Question on type 3, guys. We also talked about in this chapter the polyatomic ions, right? So polyatomic ions are groups of nonmetals that have charges like NO3 minus, NO2 minus. Again, the nitrogen and the 3 oxygens are the nitrogen 2 oxygens here, all have a -1 charge. They are held together by sharing of electrons like we drew in our Lewis structure just a second ago. This guy is nitrate, ATE. This guy is nitrite, ITE. Typically in a group of 2, the one with the most oxygens will end in ATE. The one with the least number of oxygens will end in ITE. There's also groups of 4, like ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. The one with the most oxygen starts with per and ends with 8, so perchlorate. Next guy would be chlorate. The 2 ones with the smallest number of oxygens would end in ite, so this would be chlorite. And the guy with the least number of oxygens in a group of 4 starts with hypo and ends in ite, so hypochlorite as well. Other variations, we sometimes will put an H plus onto something. So like HCO3 minus, that is what is known as hydrogen carbonate. Or it is sometimes referred to as just bicarbonate. Most of our polyatomic ions, because they are negatively charged, will usually find themselves hooked up with a metal, which means we basically default back to our type 1 and type 2 rules. If the metal needs a Roman numeral, you should put it. If it does not, then obviously you should not put it. Also, if you do have more than one polyatomic ion in a formula, you do need to put parentheses around it. So if you had something like this, that is ammonium sulfide. Because we need 2 of the NH4 pluses, we do need to put parentheses around the polyatomic ion and put the number on the bottom. Question on polyatomic ions there. Lastly, in terms of naming, I think we talked about acids and how to properly name acids. When we're talking about acids in terms of naming, it's all about whether or not there is oxygen. If the answer is there is no oxygen, it starts with hydro something ic acid. So HCl, no oxygen, would be hydrochloric acid. If it does have oxygen, it will contain one of those polyatomic ions. which ends in either ate or ite. And if it does end in ate, your acid would be something ic acid. If it ends in ite, it will be something OUS acid, no hydro on these guys with the oxygen. So HNO3, NO3 is nitrate, which means this is nitric acid. HNO2, that is nitrite, ITE. This would be nitrous acid in that particular case. So again, hydro just for our guys with no oxygen involved. Any questions on naming? I think that is chapter 5, if I'm not mistaken. Okay, so then we were off to chapter 8. And in chapter 8, we did something, I don't know, involving chemistry. Right? All right, so chapter 8, we talked about atomic mass. And remember, chapter 8, atomic mass, we actually talked about how we calculate the number on the bottom there for atomic mass. And to calculate the atomic mass, which is really the average mass of all the naturally occurring isotopes, we take the percent abundance of isotope number 1 and times it by the atomic mass of isotope number 1. We then add it to the percent abundance times the atomic mass of isotope number 2. And then you continue that pattern if you add more. And that again is how we get to those numbers that we do see on the periodic table. We also talked about in this class or chapter here, we talked about, I believe, Avogadro's number in this chapter. Avogadro's number is 1 mole of anything is 6.022 times 10 to the 23. These could be atoms. These could be molecules. The unit really does change a lot. We use this really as a conversion factor to go from moles to atoms, our molecules. So we also talked about molar mass in this chapter. Molar mass is grams per mole, and that is found from the periodic table. We basically can take this atomic mass and use it as our molar mass, because numerically equal to each other is the atomic mass in AMU to the molar mass in grams per mole. And obviously that is our conversion to go from grams by dividing by the molar mass to moles. Or opposite, if you have moles, timesing by the molar mass to get to grams. So again, obviously, as you know, those are 2 really important calculations. Typically, when we pull the molar mass off the periodic table, it is 4 significant figures that we go with. In this chapter as well, I believe we talked about different types of formulas, if I am not mistaken. We talked about empirical formulas, which is the simplest set of whole numbers of what is present, as opposed to our molecular formula, which tells us exactly what is present. So, if we had C4H16 as our molecular formula, that is 4 carbons to 16 hydrogens. We can reduce it down to CH4, which would be our empirical formula. That is the simplest ratio of what's present. We also talked about in this chapter how to sort of calculate the empirical formula from information given to you by using, so a lot of times, the percent composition by mass. So the percent composition by mass, basically you take the mass of the element you're interested in divided by the mass of the substance times 100%. And when we use something like this to calculate the empirical formula, the first thing we want to do is convert the percentage into grams. So we could assume that we have 100 grams just to keep the numbers the same. We then want to convert grams to moles. Once we have that, we want to divide by the smallest number of moles. And if we do that and we hit whole numbers, then we have our empirical formula. So again, for example, if we figured out we had 4 moles of A when we did this step here, and 2 moles of B, and we divide everybody here by the 2, which is the smallest number, that would give us 2 moles of A and 1 mole of B, which means our empirical formula would be A2B in this case, would be our empirical formula. Remember though that if you do divide and you do not hit whole numbers and it's not really close, you do have to kind of figure out a factor to multiply everybody by to get to a whole number. So if you divide and you had 2.5, you need to multiply everybody by 2 to get you there. We also, once we have the empirical formula, we could use the empirical formula to figure out the molecular formula by you need your empirical formula. You then need the molar mass of your empirical formula. And you need the molar mass of the compound. Now in book problems, this one is usually provided to you. You may need to calculate these guys here. But once you have all 3 of that information, you take the molar mass of the compound. You divide it by the molar mass of the empirical formula, and it will give you a number. And that number you multiply your empirical formula by. So if we use the one from the previous slide there, A2B as our empirical formula, and let's just say we did this and we got a 2, we would take our empirical formula and multiply everybody by 2, and that would give us A4B2 would be our molecular formula in this case. So it will typically give you a factor to multiply the empirical formula by, and you then can figure out your molecular formula. The only place where you could really round, even maybe if it's not super close, is in this step here. When you get this number, since there really should be a whole number factor, you can round to the nearest number. Sometimes in problems, they'll give you like a range of molar masses. So, you know, say, hey, it's between like 100 and 120. So the number may not come out perfect. So in that case, you can round. Any questions on that? There's chapter 8. Yeah, so that's what I was saying. You have to sort of multiply by a factor. So if you did the step where you divided everybody, you know, by the smallest number of moles, and let's just say in my example, then we ended up with like, you know, like 1.33 moles of A and 2 moles of B, for example. That would give us an empirical formula of 1.33 and B2. This is not good because they do need to be whole numbers. So you could take something like 1.33 and times it by 1, obviously gives you 133. 1.33 times 2 gives you 2.66. 1.33 times 3 gives you 3.99, which is pretty close to 4. So what you would want to do is actually multiply it by 3. And when you do that, that will give you A4 and B6 would then be your correct empirical formula to clear it. Sure. Yeah, there, yes. Ethics. Okay, wait, there you go. Yeah, no, yeah. So we're actually multiplying by the factor, not what we get there. So that's what we got on the first one, which would be 4. So it would be A4, B6 would be correct in that case. Yeah. Other questions on that there? All right. Well, I think we made a nice dent, I suppose. Yes. Any other questions or anything that I could help you with? We got through a good chunk of it. Hopefully this was helpful to you.